So we just found out that the volume for a single cylindrical shell can be written with this formula. V equals 2 pi r h delta r. Oh goodness, that's a lot of letters. So it's twice pi. I'm always expecting a pi when I work with circles. I have the radius of the cylinder. And again, this is the average radius. Because my cylinders will be very, very thin, I can make a bit of a dodge there. I'll have the height of the cylinder, and I'll have the thickness of the cylinder. So, well, hey, that's my circumference formula out in front. My volume is going to be equal to circumference times height times thickness. Ah, very good. That's a formula I can remember. I expect volume to be a three-dimensional quantity, and here I have 3 dimensions multiplied together, right? Circumference is a length, height is a different kind of length, thickness is then a third kind of length. Multiply the 3 of them together, and it is volume that I must be measuring. So, remember the problem that we started with. We got so bogged down talking about geometry. The goal of this is I have some solid whose volume I want to compute. Here, I have a function y equals f of x, and it's defining a region in the plane between x coordinates a and b. When I put that on my pottery wheel and spin it around so very fast, I see this sort of jello mold shape up here, right? So I'm taking this and I'm spinning it all the way around the y-axis like so. What does it look like when I approximate the volume of this solid? Well, I'm going to pick particular x coordinates and I'm going to use them to build these shells that I've been talking about. So let's take a look. We're going to divide the interval up into sub-intervals. Let's say there's n of them. Maybe your n is 4. Maybe my n is 10,000, just some finite number. And each one of them, there's going to be some sampling point, the usual left endpoint, right endpoint business. But their thickness is what I will call delta x. That's the thickness of my interval. And filling up this solid region with my approximating cylinders looks a bit like this. So there's a lot going on in this picture. Notice I still have the very same f of x function graphed here at the top. I've picked a particular x coordinate here, and I use that to construct one of these cylindrical shells. That's just a single one of them. Here at the bottom, we've drawn in all of the cylindrical shells together. You know, maybe this is not a shape we see every single day, or maybe it is, depending on what 80s bands you're into. Here's some other odd fellows who like to dress in this way. But that's more of an aside. In the limit, as I take more cylinders, this approximation of the volume gets better. It starts off as a fairly poor approximation if I only use 1 or 2 cylinders. But each volume for each one of those cylinders follows the same formula as in my previous video. So for each one of these cylinders, I need to calculate circumference, height, and thickness. Well, thickness is governed by my delta x. That's just the width of the interval I'm taking. Height is governed by my f of x. I am building these cylinders to be f of x units tall. Now, what is my radius here? It's got to be x. So with the correct subscript and all, we're saying that the volume of the slice I, volume of the shell I, if you prefer, is twice pi times xi bar, right? This could be the left point or the right point or the midpoint. Take your pick. That's our circumference. The height is the function f evaluated at my choice of xi. And the thickness, as always, is delta x. What do we have left to do but to add up all of those slices? So here in Greek letters is my Riemann sum. This is my chunky macro level operation. This is my approximation to the true volume. And when I take the limit as n goes to infinity, it is the limit of the Riemann sum, which defines our integral. Every single integral has a secret limit just waiting underneath the hood. But since we have antiderivatives now and fundamental theorem of calculus now, we don't have to compute that limit every single time. So I'll say, as usual, that my delta x becomes a dx. My capital sigma in Greek becomes an s in Latin. So this Riemann sum is going to tend towards the value of this integral. I'm integrating from a to b. My integrand is 2 pi x f of x dx. This is our new volume formula.